In this lesson, we're going to use quadratic equations to solve several problems. Here's our first problem. A rectangle with area of 42 square inches has a length that is 1 inch longer than the width. What are the dimensions of the rectangle? Well, I know you can probably do this one in your head, but just to show how the quadratic formula can be used, we're going to start with one that we can also do mentally. We start by drawing a sketch of a rectangle. And then we label the width x, and since the length is 1 inch longer, we label the length x plus 1. And we know that the area of a rectangle is length times width. So our equation then is x for the width times x plus 1 for the length is equal to 42. And then we apply the distributive property and add negative 42 to both sides, and we have a quadratic equation that can be factored. X minus 6 and x plus 7. So we split that into two equations. Either x minus 6 is 0, therefore x is 6, or x plus 7 is 0, so x is negative 7. But of course, a negative number can't be the length of a rectangle, so we cross out the negative 7, and so our answer for x is 6. And then the length is x plus 1, or 7. So the answer to this problem is that the rectangle is 6 inches by 7 inches. Here's another similar problem. A rectangle with area of 66 square inches has a length that is 8 inches longer than the width. What are the dimensions of the rectangle? Well, the quadratic formula helps here because this problem does not come out even. We draw our sketch, we label it x and x plus 8 for the width and the length. And then we set up our equation, apply the distributive property, add negative 66 to both sides, and that's not factorable. So we'll plug it into the quadratic formula. A is 1, B is 8, and C is negative 66. And then we apply order of operations. We do the 8 squared to get 64. And 4 times 1 times negative 66 is negative 264, but we're subtracting negative 264. So we've written that as add 264. And then for our denominator, it's 2 times 1, or 2. And then 64 plus 264 is 328. And it looks like we're going to need a little more room, so we'll go to a new slide. And we're looking to see if there's a perfect square that goes into 328. And there is. It's 4. So 4 times 82 makes 328. And since the square root of 4 is 2, we'll take the 2 out of the radical symbol. And now we can factor a 2 from the negative 8 and the 2 root 82 as shown. And then the 2's mark out. And we're left with an exact solution that x is negative 4 plus or minus the square root of 82. But we examine that plus or minus symbol. That means that one of the two solutions is negative 4, take away the square root of 82, which is clearly a negative number. And we can't have a negative number representing the length or width of a rectangle. So we're only going to concern ourselves with the other solution, negative 4 plus the square root of 82. That's the width. Well, the length is 8 more than that. So we write the expression negative 4 plus root 82 plus 8, and then we simplify it to get that the length is 4 plus root 82. And that goes with the width, which we already knew, is negative 4 plus root 82. But when we're actually working with the rectangle, we would probably want to make the rectangle, and we're going to have to decide what we can round it off to. We get our calculators out, and we round to the nearest tenth, and we get that the width is 5.1 inches, and the length is 8 more than that, or 13.1 inches. So our rectangle is approximately 5.1 inches by 13.1 inches. And just for fun, we check our work by multiplying those two numbers together, 5.1 times 13.1, and we get 66.81. So we're nearly a square inch off from our desired 66 square inches, as mentioned in the problem. Well, then we decide, well, why not round to the nearest hundredth? And that's shown here. If you round to the nearest hundredth, instead of 5.1, you get 5.06, and instead of 13.1, you get 13.06. Multiply those two numbers together, and you're pretty close. you get 66.08. So you're pretty close to 66 square inches. But of course, if you were getting a ruler out and trying to measure a length and a width to the nearest 1/100th of an inch, that would be quite a challenge. So probably measuring to the nearest tenth is the most realistic for this problem. Well, let's try one more. The length and width of an 8-inch by 10-inch rectangle were each decreased by the same amount to create a new, smaller rectangle with an area of 35 square inches. What are the dimensions of the new rectangle? Once again, we draw a sketch of a rectangle. This one's 8 by 10. But then our new one, we reduce the 10 by a number, 10 minus x, and we reduce the 8, the width, by the same number, 8 minus x. So of our new rectangle, we have the length times the width is equal to 35 as shown here. It's a pair of binomials with a product of 35. Well, we multiply the two binomials together to get 80 minus 18x plus x squared. We then write it in our more customary order by writing the x squared term first. We applied the commutative property in order to do that. Then we add negative 35 to both sides to get x squared minus 18x plus 45 is equal to 0. And this one is factorable. X minus 3 for one binomial, x minus 15 for the other. So we can break this into two equations and do the work in our head. If x minus 3 is 0, then x has to be 3. If x minus 15 is 0, then x has to be 15. But of course, if you take the 15 and substitute it for x, you'll have 10 minus 15, which is a negative number, and 8 minus 15, which is also a negative number. So the 15 can't be used here because you can't have a negative number represent the width or the length of a rectangle. So our solution for x is 3. And when we plug that in, 10 minus 3 is 7, 8 minus 3 is 5, so the new rectangle is 5 inches by 7 inches. Quadratic equations can sometimes be used in solving problems about the area of rectangles. When you are able to express one of the dimensions of a rectangle in terms of the other, it is often possible to set up an equation based on the formula for the area of a rectangle, which is, of course, length times width is equal to the area.